Thank you very much for the lovely introduction. I'd like to thank Celestine for introducing me, and also Leila Sorkati for inviting me to give this talk. So as mentioned, I've had a couple of biggish research grants, and this talk is about the work I did for one of them. So mostly I do research in finite groups, but I do some small amounts of research in infinite groups. And so today is going to be more about infinite groups, just because I think it makes for a nicer talk. So you don't need to know any group theory really to understand what I'm talking about today. So let's start. And I'm going to tell you about a family of groups to start with called free groups. And you don't need to know what a group is because I'm going to tell you. So we start by picking some set X, and I'll call the elements of X letters, or I'll sometimes call them generators, but it's just a set. Could be finite, could be infinite. So for a running example, I'll have X being the set of A and B, just two things in it. What we're going to consider is all words of finite length over, well, first of all, the symbols in X, but also we're allowed to take symbols from X and put a little -1 on them. So just a string, a finite sequence of elements. The only important thing is that it's finitely long. So for example, for our given X up there of A and B, one string or one word might be A, B, A inverse, which I've pressed down to A to the -2 to make it look shorter, and then a B, and then an A, and an A inverse. So we care about the sequence in which they come, and each thing is either one of the things from X or one of the things from X with a -1. An important word that we'll consider is the word of length 0, so the word with no letters in it. Now I need to write something on the page to talk about a word with no letters, and so I'll write it as 1, and it's just the empty word. That on its own would not be a group in any sense, but we're going to define a funny kind of equality on it. I'm going to say that two words are the same, so I'm putting an equivalence relation on them, if I can go from one of the words to the other by either deleting or inserting, either way around, pairs that look like a letter followed by its inverse, or the -1 form followed by X. So either way around, so either A inverse or A inverse A, or B inverse or B inverse B, and I'm allowed to put it in anywhere and also take it out anywhere. So if we look at the example that I had before, A to the -2, B A inverse, we can see that I could put in a B inverse at the beginning if I want to. I can put in a B inverse after the first A, that's allowed. And those two words would be equal. And I can also delete the A inverse from the end, and that's allowed. So these two count as the same word. They're in the same equivalence class. I say that a word is freely cancelled if it's got none of these special subwords in it. So if I've removed all of the special subwords. So for the example we've got above there of A, B inverse, B A to the -2B, that's not freely cancelled yet because it's got a B inverse in it. But if I get rid of the B inverse, I get down to just A, B, A to the -2, and B, and that is freely cancelled because we can't see anything next to its inverse. Every equivalence class of words is going to contain one of these freely cancelled words because you just take out the pairs, and it's a fairly easy exercise to show that it doesn't matter what order you take them out. I multiply words, so a group is a set with some way of multiplying that satisfies some axioms. So what's the multiplication? Well, the multiplication is literally you just write one word followed by another word. So W1 times W2 is just write the two words out next to each other. But of course, having done so, you might find that the resulting word is not freely cancelled, so you might choose to cancel it down afterwards. So for example, A squared B multiplied by A is just A squared BA. So there's almost nothing to see there. If I were to take another word though, so say I took BA and multiplied A inverse, well, maybe I'm going to find the shortest representative for it, and we spot that there's an AA inverse in the middle of the word, here, A followed by AA inverse, And if we get rid of that, then there's a B followed by a B inverse, and we get rid of that, and we're all the way down to the special word, which is the empty word 1. So you can see there that I could have said that the inverse of a word, AB, say, is what you get by just writing it backwards and inversing each letter. Because if I do AB times B inverse A inverse, the B cancels with the B inverse, the A cancels with the A inverse, just like I had here for BA. So a group is a set with a multiplication, and one of the things we require ourselves to be able to do is find inverses that get us back to 1. And so I've now just proved that you can do that. The final condition for being a group we don't need to worry about. So the resulting object is a group. So this set of words with this funny equality of being able to add and delete XX inverse pairs, and with multiplication being concatenation, that's a group called f of x, where capital X is the set we're working over, and it's also called the free group on X. So that's our first group. Well, that's infinitely many groups because we can pick infinitely many different sets X. But if I was just studying free groups, that would be quite specialized, and I'm trying to give a fairly general talk today. So let me show you how we can go from free groups to any old kind of group. So we're going to do so by, first of all, picking a subset. So we've got our group f of x, which is just these words over x with the particular relation of equality on them. We pick a subset, which I'll call curly R, and that's a set we'll call a set of relators. So I'm going to run with the example we had before of x being AB, and I'm going to pick as a relator A, B, A inverse, B inverse, just one. Now I'm going to say that a word is freely cyclically cancelled if it's freely cancelled, so it doesn't have any XX inverse pairs, and it's not of the form beginning with an X and finishing with an X inverse, or beginning with an inverse and finishing with an X. Don't worry too much for now, but it's important to assume that the elements of R are freely cyclically cancelled. So if you look at the example I've given, it begins with an A and ends with a B inverse. Those are different letters, so that's fine. So given f of x and R, so given x and R, I'm going to define another group, G. So it's a set with a multiplication on it. So I need to tell you what the set is. Well, I start just like I did with f of x by taking all words over x together with x inverse. So all of the words I can write which have letters from x or letters which are from x but with a little -1 sign on them. The equality is the weird one. So two words are going to be equal. I'm putting an equality relation on these words. If I can go from one to the other, well, firstly, the same condition as before. So I can insert and remove pairs of things next to their inverses, but I can do more now as well. I can also insert or remove elements from my set R, or the inverses of things in my set R. So the inverse of this would be B inverse, A inverse, because you read it backwards. So in this group that I make by taking f of x with R, I can make two words equal by inserting and removing either XX inverse pairs or this thing that I've written down there, that word R, or its inverse. We multiplied just like we did for the free group by concatenating, so you write one word next to the other. And just like on the previous slide, to invert an element, I just write it backwards and put minus signs on. So again, it's an undergraduate exercise to show that this does give us a group. There's only one further condition you have to check, which is what's called associativity, but it goes through. So let me do it as an example. So if my group G is the one that we've just made, so here's my set X, that's AB, and here's my relator, AB, A inverse, B inverse. What can happen now with the equality? So if I start with the word AB, say, well, I can get to other words by inserting and removing AA inverse or BB inverse or B inverse B or which one have I missed? A inverse A, or elements of R or their inverses. So from AB, I'm allowed to put an A inverse A on the end, and those two words are equal in the group. And from there, I can stick a of my A inverse A. Then I can notice that the first 4 letters now look like A, B, A inverse, B inverse, and that's the same as my relator R was, and so I'm allowed to delete that. And so we see that in this group G, AB is the same thing as BA. Right, so this is lots of ways of making groups. Let me just convince you that this is really, really interesting by saying that, so this object I've just made is a presentation and it's finite if the things are finite. Well, it's an easy theorem that every group can be defined by one of these. Let me prove it for you. Take as the set X all of the elements of the group. So that might be quite a big set if the group is infinite, but we can take that as our set X. And take as the relators are all of the rules for multiplying in a group. So if one element, if G1 times G2 is equal to G3, then that means that G1, G2, G3 inverse is equal to the identity. And so I put that into R. If I take all of the group elements and all of those rules, and then I wind up defining the group that I started with. So every group can be defined by a presentation, which means that if I study groups given by presentations, I'm studying all groups. I'm going to be particularly interested in computational examples though. So for those, I'm going to need to work with finite sets X and R. So I'm going to be interested in groups that are finitely presented. Now, the most basic thing we might want to know about a group if we were working with it is this element the same as that element? Are these two things equal under this funny kind of identity? Because if I can't even tell two things apart, then it's not clear what it means by knowing anything at all about the group. So let's just notice if two words are equal, so suppose they're equal, then I can multiply, I'm not good at left and right, I can multiply on the right by W2 inverse on both sides. So on this side, I'll wind up with W1, W2 inverse, and on this side, I'll wind up with W2 times its inverse, which is the identity. So if I can understand when something's equal to 1, so when it's equal in the group to the empty word, then I can understand when any two elements are equal. So the most basic thing we might want to understand about our group is when two elements are equal. And to answer that question, it's enough to be able to work out whether or not something is equal to the empty word, whether or not something is equal to the identity. One more technical definition. So the conjugate of a word W by a letter X is X inverse times W times X. And then here's a theorem that goes back a long way. Let's take G being given by a presentation like that. So it's finitely presented, X and R are finite. And let's take some word made over the right letters. So it's a product of elements of X and their inverses. Then W is equal to the identity in G if and only if. So this is a two-way condition. So we need to understand when words are equal to the identity in G. It's going to be equal to the identity in G if and only if it's equal in the free group. So that was the easier to understand group, to a product of conjugates of things from R and their inverses. Now, one direction of this is really easy. So if something is a product of conjugates of relators and their inverses in the free group, then we know that in G, I can delete the relators and I can delete their inverses. And if I delete relators and their inverses, all I see left is the conjugating elements, and I can delete little pairs, XX inverse as well. So that gets me down to 1. The converse direction is a little harder, but not too much. So understanding when a word is equal to the identity means being able to understand when it's equal to a product of conjugates of relators and their inverses. All right, let's go slightly algorithmic now. So we're going to look at stuff done by Max Dehn. And I'm interested in decision problems. So those are questions, mathematical questions where the answer is yes or no. So where you're not asking someone to construct something or give an example of something, you're just asking for yes or no. Well, still in the world of my group, Max Dehn, all the way back in 1912, so this is well before computers were invented and well before we really knew what algorithms were or anything like that, posed 3 problems which are decision problems. So the first problem that was important was the word problem. And that's exactly the problem I've just been talking about. So you're given some word in f of x, and you're asked to decide algorithmically whether the word is equal to 1. So we want to come up with an algorithm where you give it x and r, and then you give it w, and the algorithm spits out yes if the word is equal to 1, and spits out no if the word is not equal to 1. Next problem posed by Dehn was the conjugacy problem. And he said, well, for this, you're given 2 words in f of x, and you want to decide if they're conjugate. So you want to decide algorithmically whether there's some element of f of x such that pre-multiplying by the inverse and post-multiplying by it gets you from W1 to W2. This is the same sort of notion of conjugation as I had on the previous slide. And the third problem is a bit harder to state, but I'll write it up. Now you're given 2 presentations, and you want to decide whether they represent the same group. So the names of the elements of the group might be different, but is it really the same? Can I send bijectively the elements from the first group over to the elements of the second so that things multiply the same way on both sides? So are they 2 copies of the same group is what the isomorphism question's asking. So all 3 of those are yes-no problems, and Dehn was able to give answers in some special cases to some of them, but wasn't able to answer them in general. So it remained an interesting problem whether we could do this. Let's just notice that if you're given this finite presentation and you're given a word you'd like to know is equal to 1, if it is equal to 1 in the group, then we can work that out by just systematically listing all products of conjugates of relators. So first of all, we say, well, is W equal to one of the relators or equal to the inverse of one of the relators? And then I might say, is it a conjugate of one of the relators by a single letter? Or is it a product of 2 relators? Or is it a product of conjugates of a single relator by 3 letters? Or product of 2 relators by 2 letters, or whatever. I could work my way out, and eventually I would find something which was equal in the pre-group to W. Unfortunately, if W is not equal to 1, then this process will never terminate. So I can get a yes this way round. I want a yes or a no, but I can't get a no. So there's an obvious one way round to do it. Right, so Dehn asked this in 1912, which is before computing. So let me move on to probably one of the biggest topics in early 20th century mathematics. So a decision problem, one of these yes-no problems, is undecidable if there's no algorithm which always terminates with the right answer in finite time. So if there is no such algorithm. So one of the remarkable things is that it turns out that we can find undecidable problems. So the granddaddy of them all is the halting problem, where you're given a Turing machine, so that's an idealized model of a computer, and some input to the Turing machine, and the question is just, will that machine stop when you give it that input? So is it going to run forever, or am I just going to need to turn the machine off at the wall, or will it definitely stop at some point? Well, Turing showed in 1936 that the halting problem is undecidable, so he introduced the notion of undecidability and showed here is a concrete, actual, undecidable problem, and along the way effectively showed that there are problems that computers can't solve. Normal subgroup. Yes, normal subgroup is the same as it always is. Praise. I just haven't needed to talk about normal subgroup yet, but yes. So Turing showed that the halting problem is undecidable, and that introduced the concept of undecidability to the world, invented it. And there was a whole industry after Turing's paper of proving that other problems were undecidable, but they were mostly problems which were quite closely related to logic, basically. I mean, so Turing's building on stuff to do with logic and foundations of computer science, and so lots of the other undecidable problems were very obviously variants on Turing's original halting problem. So it was quite remarkable when Novikov and Boone, independently in the 1950s, showed that in fact there were groups with undecidable word problem. So there are finite presentations of the sort I showed you on the previous slide, where there is no algorithm to show in the group. So the fact that, because it can't give a no, is kind of irrelevant. I mean, I might just be being stupid and not have come up with a good one. But what Novikov and Boone showed was, in fact, there exist groups where there cannot be such an algorithm. And they're not even very complicated looking, these groups. If you look them up on Wikipedia, there's an example due to Don Collins that's got 12 generators. So X has got size 12. And the number of relators is 20 something. So not huge, doesn't look crazy complicated, but it's provable that you cannot design an algorithm to solve the word problem in that group. Well, once undecidability gets somewhere, it infects everything. So the second of Dehn's problems, so this says the first of Dehn's problems is undecidable. The second of Dehn's problems, which was the conjugacy problem, says, can I pre-multiply a group element by something inverted and then post-multiply it by the original thing and reach the other one? Well, if I could solve that problem, then I could show that a word is conjugate to 1. So I pre-multiply W by something inverted, and post-multiply it by something, and I get to the identity. Rearranging that would mean that my word W was equal to 1, which would mean that I had solved the word problem, which I can't do. So the conjugacy problem is also undecidable. And then it turns out that loads of other problems are undecidable. So Dehn's third problem, the isomorphism problem, is undecidable. Things which seem like they ought to be easy. So deciding, given a finite presentation like I've just been talking about, whether everything is equal to the empty word, that's undecidable. So is there really just a single element in that group is undecidable. So undecidability somehow gets everywhere once it's started. I will come back to the computational stuff towards the end of the talk, but let me talk now about how do we work with these presentations. So we work with them very pictorially, which makes it nice for talks. So kind of diagram I want to start out by talking about, it's called a Van Kampen diagram.
Excuse me. There was one question in the chat saying that is the notion of normal subgroup the same as the undecidability problem?
No, so normal subgroup is a particular kind of group inside the group. I don't need normal subgroup for this point. Yeah, so there's no normal subgroup on this slide. But yeah, a normal subgroup is a group that is closed under conjugacy, just like it normally is. But I'm not going to need normal subgroups for a while. So yeah, a Van Kampen diagram over a finite presentation is, I'm being slightly dodgy with the definition here, but it's a graph. So a graph in the sense of vertices and edges. So we've got some points and some pairs of points, which are our edges. It's a plane graph, which means I've drawn it in the plane. I've drawn it on a flat surface with no edges crossing. It's finite and it's connected, and indeed simply connected. So once I've drawn it on the plane, that means it's got a single external face and all the other faces are internal. I'm going to think of each edge of that graph. So strictly speaking, an edge is just a pair of vertices. But I'm going to think of it as being made of two directed edges, oppositely oriented, which I'll call half edges. And the edges are going to be labelled. So one side of the edge will be labelled with one of my generators, and the other side has to be labelled by the inverse. Since this is a graph that's been embedded in the plane, there's an external face, but all of the other faces have to be labelled as I read around their edges by elements from my relator set or their inverses, and let's say reading clockwise. It doesn't matter as long as we fix a convention. So there's a label on each edge, and as I work my way around the face, reading the labels on each edge, I have to either see an element of the relator or I have to see an inverse of a relator. And then the label of the boundary, so there's a unique external face, and so there's a single boundary, that label has to be these words freely cyclically cancelled, which I used back at the beginning. So the label of the boundary has to not have any XX inverse pairs. And since it doesn't, freely cyclically cancelled, it kind of reads like a cyclic word because the boundary is a cycle, it doesn't really have a beginning and an end exactly. So let me draw a picture of one of these because that's quite a lot to take in one go. So if I had as my group a 3 generator, so A, squared b, a inverse cb, and ac to the -3. Well, here's a word over abc, ca squared c. And it turns out that that word is equal to the identity in the group. Not very obviously. Praise is asking, with the conjugacy problem, does it mean that the group is not the distinct union of conjugacy classes? No, the group is still a union of conjugacy classes. We're just asking if two elements of the group are in the same conjugacy class. So the conjugacy problem is exactly saying, are these two elements in the same conjugacy class? So yeah, my word can be written as C inverse with one of the relators in between, C inverse with the inverse of this relator in between, and this is effectively a conjugate of C cubed A inverse, which is the inverse of this relator. And to see that that's the same as W, notice that I cancel the C inverse with the C, the B with the B inverse. Remember, we've got a CA squared there. C inverse with the C, the A with the A inverse, this C inverse with this C, and all I've got left is CA squared and a C at the end. So those are the same words in the group. Right. Here's a picture. Here's the Van Kampen diagram for W. So it's a graph, there's some edges and some vertices. Each edge, I've put the positive label on one side, and you should think of the inverse as being on the other side. So I've written it on the side where it's positive, and the inverse is the other side of the edge. If I read around this diagram, I read CAAC, which is W. But if I read around each individual face, so let's take this one here, I'm going to see A, because the A is on this side, C inverse, because the C is on the other side, C inverse, which is exactly this relator here. If I read around this face, I'm going to see A inverse CB, which is this relator. And if I read around this one, I'm going to see B inverse, A inverse, which is the inverse of this one. There is a way to demonstrate how you make W from this expression, which I won't do. But anyway, this is what a Van Kampen diagram looks like. Right, so those pictures are quite pretty and they give us a way of thinking about things. They also give us a way of approaching the word problem directly. So the reason I'm calling them Van Kampen diagrams is they're due to Van Kampen. And he proved back in 1933 that if I've got some word over the generators that's freely cyclically cancelled, so we don't see any XX inverse pairs anywhere, and is equal to the identity in the corresponding group, then it is equal to the identity in the corresponding group if and only if it's the boundary word of one of these diagrams. So if we understand these diagrams, then we understand all of the words which are equal to the identity. And if we understand all of the words which are equal to the identity, then we understand all the words which are equal to each other. So if a word is equal to the identity in the group, then its area is the minimum number of faces, sorry, I've misspelled minimum, in a diagram proving it. So on the previous slide, we had some faces. So here, W's got area 3. CA squared C has area 3 because I've managed to prove it with 3 faces, and you can convince yourself that I couldn't have proved it with fewer than 3 faces, so I couldn't have done it with just 2. So that's what the area is. The length of the word is just the number of letters, but I take it down to a freely reduced form before talking about its length. Then the Dehn function, so this is named after Max Dehn of a presentation. It's a function that goes from the natural numbers to the natural numbers, and we send each number to the largest area of a word that is equal to the identity and has length at most, the n that we started with. So we'll send 1 to the largest possible area of a word that's equal to the identity and has length 1, at most 1. So typically that's going to be 0 because normally single elements are not going to be equal to the identity. If I can bound the Dehn function, so if I can find an upper bound on how many faces in the diagram, Then we can, because the silly algorithm I gave for solving the word problem before, where I said we just look for our word W by testing longer and longer conjugates of relators, the number of conjugates I need to take is its area. So the number of relators that appear is its area. So if I know an upper bound on how many relators, I can also get an upper bound on how long the conjugating elements are, because they have to fit in one of these Van Kampen diagrams. And so I can make my algorithm say no as well as yes. I can tell when I've looked at enough words. This is not an algorithm you would ever want to run, but it would stop in theory. Now, it turns out the actual Dehn function of a presentation depends on what presentation you've written down. But it turns out the exponent that appears, so is it a linear function? Is it something like n goes to lambda n plus c for some constants lambda and c? Is it a quadratic function? Is it an exponential function? That depends on the group, not the presentation. So a group can have lots of different presentations, but the growth rate of them doesn't depend on which presentation you pick. It just depends on what group you picked. Right, Cayley graphs. Here's another way of drawing pictures from groups. So let's start with a group with a generating set X, and I'm going to assume that X is inverse closed. So X is the same thing as X inverse, and that 1's not there. So this is a bit different to how I had it before, where I had X and then I put inverses on it. Now I'm going to assume that all the inverses are already in there too. Then the Cayley graph of the group with respect to that set is, again, a graph in the sense of Van Kampen diagram. So we've got vertices and edges. There'll be a vertex for each element of the group and an edge, so a pair of vertices, if and only if there's one of my generators where if I post multiply by X, I get from G to H. So I can go from G to H in my graph if I can use an element of X to get from G to H. I've made an undirected graph by assuming that X is equal to X inverse, because if I can get from G to H by multiplying by X, then I can get from H to G by multiplying by X inverse. So the edge is both directional. Here's part of the Cayley graph for a free group. So I'm doing it with respect to the obvious generating set. So here's the identity in the middle. And then I've put all the A edges going up the way, and I've put all the A inverse edges, let's say, going down the way, and the B ones going out to the right, and the B inverse ones going to the left. And I haven't actually bothered labeling the directions, but hopefully that's clear enough. And you can see this is going to be an infinite object. I've drawn it a bit like a fractal with the distances halving each time, but this thing's going to go on forever. Every single vertex will have degree 4, because you can leave any group element by multiplying by an A or a B or an A inverse or a B inverse. All right, so Cayley graphs let us get into another bit of mathematics. So we're still wanting to understand groups with finite presentations, and they do have generating sets like this, so we can make these Cayley graphs. We can turn any Cayley graph into a metric space. So a metric space is a space with some distance function on it that behaves like a distance. And we say that a metric space is geodesic if for any pair of points in the space, there's a path between them, so I can get from X to Y without leaving the space, of the right length. So a metric space is just a space with a distance function on it, and I want to be able to find a path in the space of length that distance. So that it kind of means there can't be bad holes in the space. The distance function has to agree with how you actually can walk around inside it. We can turn a Cayley graph into a geodesic metric space. So naturally, a Cayley graph is just vertices and edges. But if I identify each edge with the unit interval, so that now this is all part of one big space, the edges are there, then I can define the distance between any 2 points to be the length of a shortest path from X to Y. And now X and Y aren't necessarily vertices, they could be halfway down an edge or 3/4 of the way down the edge. So I'm taking the space together with all of its edges. I've got the vertices, each edge has length 1, we're taking all the points along the edge too. So here's a bit of the Cayley graph of Z cross Z, which is, if you don't know what that means, don't worry, it's the one I was talking about before, A, B, A inverse, B inverse. So starting at 1, I can go out with an A, up with a B, back with an A inverse, and back with a B inverse. I've drawn in here 2 geodesics to the point A squared B inverse from 1. down the way, and then 2 A's out the way, and then come down by 1. Or I could have done the path through the middle, which I didn't draw in, which would also have length 3. So here's a bunch of geodesics. They're paths of length 3 for getting to something that is length 3 from 1. If I were to go all around a bunch of other vertices, that would not be a geodesic. Now, it turns out that many properties of Cayley graphs, and I'm not going to list them all, but many properties of Cayley graphs, although I've defined it with respect to a particular generating set, they don't care what the generating set is. So, for example, any graph, Cayley graph for a free group looks tree-like, and this is a kind of Gromov phrase, from far enough away. So if you stand very far back, and if your eyesight's not very good, it's going to look like a tree. It might not be a tree close up if I've picked some weird set of generators, but it will look like a tree from far enough away. And any Cayley graph for this group, I've made it like this, but if I made the same group differently, it would look grid-like still. All right, let me talk about metric spaces a bit more. Well, in a geodesic metric space, I can make triangles. A geodesic triangle is, well, it's a triangle, 3 points and 3 geodesics between them. So a triangle's got 3 corners and 3 edges. And we say that a triangle is delta slim if from anywhere on any of the sides, the distance to one side or the other 2 is at most delta. So as I work my way along the edge AB, I can always get to AC or BC, I don't know which, one or the other, within delta. So triangles being delta slim means they look squished, like I've just drawn it there. They look skinny. A delta hyperbolic space is a geodesic metric space. So space, distance function, paths between points of the minimum possible length, in which every geodesic triangle is delta slim. So all triangles are skinny. It's kind of magic that such a thing exists, but hyperbolic space exists, and this is the definition of hyperbolic space. And one of the cute things about hyperbolic space is that area doesn't, so in Euclidean space, the space in which we live, area of say, triangles grows quadratically as the boundaries get longer. In hyperbolic space, area grows linearly. So here's a picture of some hyperbolic space. You want to imagine that every single one of these shapes is actually the same size as all of the other shapes. It's just that I'm trying to draw them on a flat plane, or rather Eshel is drawing them on a flat plane, so they don't look like they're the same size because he's having to squish them in. But you can see these skinny triangles coming around here, and you can maybe see that as we try and make triangles further and further out, the distortion is going to grow and grow and grow. The triangles are going to look skinnier and skinnier and skinnier. But if you take all of these shapes as being the same size, so here's our central 6 of them, they're all the same size, it's just the way I've had to represent them to draw them on the plane. This is what hyperbolic space looks like. Hyperbolic space is made up of skinny triangles. So from a point here to a point here is a very, very long distance, because all of these tiny shapes are actually the same size as this. It might well be quicker to come in and then go out again to get from one of these points to another. Right, finally, hyperbolic groups. So Gromov defined a group to be hyperbolic if there exists some delta such that the Cayley graph for the group, so I've drawn you Cayley graphs, so we draw the Cayley graph for the group, if that Cayley graph is a delta hyperbolic space, so all of the triangles in the Cayley graph are skinny. I'm going to try and convince you in the end of my talk that this is an interesting and useful definition for all connecting to all the things I've shown you before. So firstly, let's see that it's kind of useful for group theorists. Gromov showed that if a group is delta hyperbolic, with respect to a particular generating set, then if I picked a different generating set, I would still find that there was some delta prime such that that Cayley graph was delta prime hyperbolic. So if it's hyperbolic with respect to one generating set, then it's hyperbolic with respect to all of them. Good, so that means that we're safely doing group theory. We're not just studying particular presentations. The next interesting point is that the Van Kampen diagrams that I showed you 2 diagrams ago, they embed into Cayley graphs. So you can map all of the vertices of the graph in my Van Kampen diagram over to the vertices of the Cayley graph in such a way that locally it's an overall you identify. But if I just look at it, then it's an embedding. So if G is hyperbolic, then Van Kampen diagrams for G look like bits of hyperbolic space, because the definition of being hyperbolic is that the Cayley graph looks hyperbolic. And now I'm saying that the Van Kampen diagrams go in there, so they look hyperbolic too. What does that mean? What does looking hyperbolic mean? Well, I said that in hyperbolic space, area grows linearly with perimeter for shapes, not like, so in Euclidean space, it grows quadratically. In hyperbolic space, it grows linearly. So Gromov showed that a group is hyperbolic if and only if it has a linear Dehn function. So given a word that's equal to the identity in the group, there's some linear function of the length of the word which bounds how many faces appear in its Van Kampen diagram. So bounds how many conjugates of relators I have to think of to show that the word is equal to the identity. Interestingly, I said that Dehn function says is independent of generating set, but that the exponent is a constant. So linear is exponent 1, right? There's no groups with Dehn function between 1 and 2. There's a gap. So you can get Dehn function 1, you can get quadratic, and once you're above quadratic, they're dense. Every single real number is a possible exponent of a Dehn function. So let me give you some examples of hyperbolic groups. Well, certainly all finite groups are hyperbolic for the trivial reason that the Cayley graph is finite. The vertices of the Cayley graph are the group elements. So if there's only finitely many group elements, there's only finitely many vertices, which means no triangle can be fatter than the total number of vertices. Fine, they're hyperbolic for a boring reason. Free groups, though, are more interestingly hyperbolic. So I've showed you that the Cayley graph of a free group is a tree on the standard presentation. So if I try and make a triangle in a tree, it's going to look just like some sticks. It's not going to have any area inside it because there are no areas inside a tree. We just go out along paths and back along the same path. So all areas are 0. So if I took some other way of making a free group, some kind of slightly messed up way of making a free group, I said that it looks tree-like from far enough away. That means I might find a little bit of area for the messed up presentation, but it wouldn't be very much. It would still be linear. A group with quadratic Dehn function, so I said there's a gap between 1 and 2, so we're not going to find anything between linear and quadratic. There'll be no groups with Dehn function n to the 1.5, say, is this running example I've had for ages now of A, B, A inverse, B inverse. I drew you the Cayley graph for that and it looked like a grid. So a grid kind of describes how the table my computer's sitting on is, and that's got quadratic area just like we have in normal space around us because it's part of it. So another way of saying that is if I were to take something, oh, I've written it with x's and y's, sorry, that should be a to the n, b to the n equal to 1. That needs n squared relations in a Van Kampen diagram proving it because I need to fill in that box on the Cayley graph. Right, Dehn's functions for hyperbolic groups, Dehn's problems. So if G is delta hyperbolic and R prime is all words equal to the identity in G of length at most 48 delta, 48 is a magic number, but it works. Then a word is equal to the identity in the group only if W contains more than half of some relator in this big set. So R prime is not the original set of relators, it's all words of a given length. So I can solve the word problem in linear time given R prime. So I can find more than half of a relator, replace it by the shorter than half of a relator, find another more than half of a relator, replace it by shorter relator. And that will solve the word problem in linear time, given a little bit of work. So Domansky and Anshel actually proved the linear time part. David Epstein and Derek Holt in 2006 proved that if G is hyperbolic, then we can solve the conjugacy problem in linear time. But again, given the right presentation, not given any old presentation. And much more recently, Domani and Girardel proved in 2010 that the isomorphism problem for hyperbolic groups, that was the third of Dehn's problems, is decidable. Not quickly, but it is decidable. But it's undecidable whether or not a group is hyperbolic. So we have a bit of an issue there. Let me just skip this slide, I think, because I want to get to the last slide. So this is what we did with the big graph. What we did was we developed Verify, which on input a finite presentation for a group G, so you give it an X and an R, it returns true in polynomial time, so time polynomial in the length of the presentation, only if G is hyperbolic, and otherwise it returns fail. So far that's not interesting, it might always return fail, but it actually returns true a lot of the time, and we can prove that. So we've implemented our procedure, and here's some run times on a free group on 100 generators, where I've picked a bunch of random relators of a given length. Time is in seconds, and I've run it on 20 instances for each, and told you how many times it returned true, just to convince you that it does often return true. So with 30 random relators of length 4, it returned true 14 times out of 20 in 0.09 of a second. Once I was up to 30 random relators of length 10, then it worked all the time. It always returned true, and again in less than a second. And I just wanted to put this grid in to show you that my algorithm is fast. So 100 generators, 70 random relators of length 50. That's a big object, and it's taking a couple of minutes to work each time. If it works, then we can construct one of the solvers to the word problem that runs in linear time. So this fast solution for hyperbolic groups. So we don't work all the time, but if we do work, we work quickly to solve one of Dehn's problems. And we've released our algorithms in Magma and Gap, and I am out of time, so I shall stop there. Thank you very much.